You did right. Okay. Well, good morning, everybody, and thanks for coming to our talk this morning. Happy to be here and to give you an update. I hope from a slightly different perspective than what you're used to seeing from a lot of things you're seeing at the show. My perspective, and our partners at Walker, what we produce and what we provide actually is the network infrastructure for the network itself. So the backbones that everybody's running over. So typically when we talk about cyber and security, we're talking about layer 3 and up, and that's still the lion's share of where the cyber issues come from and where you have to protect yourself. But I do want to talk about how that influences the lower levels of the network, and actually some of the things from a security perspective that can actually be addressed at the lower levels of the network. So hopefully you've seen the abstract. That's why you're here. But that's really the different thing that I want to talk about today that I hope is somewhat unique and gives you a little bit of a better perspective on how some of these things impact the lower layers of the network, layer 0 through layer 2 and layer 3. I wanted to start by just giving a little background on some of the things that are actually influencing the architecture and the capabilities of the underlying network. And so we'll go over that first, and then talk about some of the automation and software capabilities that we're layering on top of this network. But it's important to understand why the network is evolving the way it is, and what's driving the capabilities and capacities really that are in the networks today and going forward. So in terms of trends that are driving the industry, and the industry I'm talking about is really the datacoms, telecoms, the overall high-capacity network industry. Historically, it was driven, interestingly enough, by none of the things that are on this chart right now. Right? It was driven by the telecoms and by voice comms, mobile, et cetera. So about the only thing that really started driving the networks, a decade or so ago, that's still there is mobility and 5G. But in terms of the things that are driving the network now, probably the largest influence we have over and above the mobility and wireless markets is cloud. There's been, in the last decade or so, an absolutely sea change in terms of who's buying network capacity and how it's being deployed. And it's really all being driven by the cloud providers with massive amounts of compute store that they're putting in data centers that they then have to deploy communications between those data centers, and we'll talk a little bit about what's happening even in 5G and how that's driving more data centers, but actually a little more decentralized, right? So we've got a couple of things going on. A lot of it's driven by cloud, and the related data centers that all support the cloud. Then there's IoT. And basically, everybody's got a processor on everything, and everything's Wi-Fi linked. So there's a lot of complexity to support the IoT devices. And as we move into the 5G generation, where we have the ability to have low latency comms with more and more items in smart cities, and smart cars, and smart everything, all of that is going to be provided by putting a number of demands on the network. And then the other thing related to mobility and 5G is what we call fiber densification, which is the movement of fiber further, deeper and deeper into the network. It used to be that fiber was just in the cores and then in the regional areas between towns, et cetera. But now with things coming online with 5G, you're going to have to run fiber to pretty much all the towers. And there are way more towers than there ever were in the past. You've got to keep them close together so you can have the high bandwidths that you want to the mobile devices. So it's driving fiber deeper into the network. So all of these things are, conspiring to basically change the overall architecture of the networks that we have today, and to really change the capabilities of those networks. So if we, look a little bit in the Wayback Machine, and honestly, the Wayback Machine doesn't have to go that far back before things look a fair bit different than they do today. So it's really a testament to the kind of changes we've been seeing in the industry. But first 15 years of the telecom revolution, so we're going way back to, the late 90s and early 2000s, right? And how did people communicate, using the network? You'll see a lot of names here that don't even exist anymore. I mean, UNet, PSINet, those of you who've been around for a little while, you remember those things. But, back then, the network was really about connecting users back to maybe their office building or other users. So it was kind of a point-to-point connectivity. And the network itself was fairly stratified. We had the local networks at the edge of the networks, moving into the local ISPs, on Baltimore. So I remember CharmNet and things like that. Then there were the regional ISPs, and finally we had the big carriers and the tier 1 backbones. And of course, layered on top of all of this, we had voice and all that. But from a data perspective, this is what we're dealing with. Flip the card into today, and what you see is the number of layers has been converged. So now we still have the customer networks and the businesses like we've always done, but we've reduced the number of layers in the network. There really isn't the local, regional, and even national stuff. It's basically converged into one layer of ISPs, which then feed the tier 1 backbones. And look at this. It's all the cloud service providers up there. And when you look at how the data is flowing through the network, that too has changed. It used to be primarily, unidirectional and bidirectional flows between different spots in the network, but those flows stayed relatively constant. Now we're in a mode where, because of all the applications that are running in the cloud and the capabilities that are in the cloud, you go up to the cloud, you do a bunch of processing, and you don't just come back down. What's less clear, at least to folks on the outside, is that when you make a request to one of these cloud providers, there's a huge amount of secondary and tertiary processing and comms that goes on to support that request. So, it's not just that the users here at the edge are requesting content, but there's a tremendous amount of activity, content to content, that's between applications that run in a variety of data centers to collect the information. You make a simple request. You told Alexa you wanted to know, what time the game was on today. Well, Alexa had to first decode your voice and figure out what you said, and then it had to figure out what databases to access and get the information, and then it had to convert it back to voice, and all that creates basically a storm of activity, much of which is contained within a data center, but a lot of it is still even not contained within a single data center. So it's ping-ponging around to different data centers and different databases, so that you can do this content-to-content capability. And oh, by the way, when we get to 5G and the latest versions, the later versions of LTE, and we start talking about wanting to do things in real time or near real time with the network, basically all these clouds, they start fracturing and becoming micro clouds that are sitting more towards the edge of the network. So, it just gets worse in terms of the amount of complexity that's in the network and the variety of different ways that folks, really machine to machine, needs to communicate. And so it's driving the network in some interesting ways. One of the first and most obvious ways is capacity, as we all know. It goes only one direction, up. And it's really going geometrically up. But a couple of interesting tidbits, particularly, many of you, I think, are sitting more towards the edge of the network than the core, but even towards the edge of the network, we're starting to see 100 gig as being the stock in trade. I mean, DISA, for example, anybody who's hanging off of DISA, pretty much, yes, they do offer low-rate services, but pretty much any base or large customer or mission that's hanging off the DISA network, they're getting a 100 gig drop. So, the amount of capacity that's available, not everywhere in the network, but in key places in the network is very large. And if you look at the underpinnings of the network, it wasn't that long ago that the entirety of the internet was run on a pair of 10 gig lines, right? But now it's multiples of 100 gigs. So things have really stepped up in terms of the capacity on the network. And you look back only a decade, and a decade ago was a preponderance of 10 gig, a little bit of 40 gig, and because of what happened in the economy and the telecom industry in the early 2000s, what we call the industry nuclear winter. 40 gig, which normally would have had a longer life, pretty much had a brief life because it pretty much just migrated to 100 gig. But a decade ago, 10 gig was stock and trade. Here we are 10 years later, and we're pretty much at the end of the 100 gig generation. Although the vast majority of the services, in terms of what you as users would consume, it's going to be 100 gig. But actually, behind the covers a little bit, in the core of the network, what are running on the individual wavelengths that carry those 100 gigs of data, it's actually moved from 100 gig to 100/200. And you can see that now. Here we are in 2019, and we're almost getting a crossover between deployed wavelengths or capacity. A wavelength is an increment of capacity in the network. So there are fewer and fewer waves now that are being deployed that can do only 100 gig, and more that are able to burst up to or run natively at 200 gig. And oh, by the way, since I mentioned DISA, what they're actually deploying is today, the DISA network, even though the services are 100 gig, they actually have the capability to go up to 200 gig per lambda. So there's almost a factor of 2 baked into many networks that have been deploying recent and quasi-recent technologies right away. And where the industry is headed is, again, another multiple, where 400 gig, kind of in the middle, where 300 to 600 gig, but honestly what's going to happen is the vast majority of the traffic on a capacity per lambda or per wavelength basis, and then that gets multiplied by the number of wavelengths in the system, but is going to move pretty cleanly, I think, from 100 to 400, and that's going to be driven by, and that's going to be driven really by the client speeds. Today 100 gig E is pretty much stock and trade for the data centers and as a client rate. These intermediate rates, 200, 250, 300, 600, there's no standard for that. We're running, as an industry, we're running that core of the network, but in terms of a client, a handoff that a user would actually get or a mission would actually receive is right now, the highest is 100 gig, but we're moving to 400. And that's going to happen over the next couple of years. So it's really starting to happen now, but it's going to accelerate. And so you're going to see, now 400 gig E off the back of switches and routers, which is going to be able to be carried natively across the wide area network itself. And the wide area network is going to consist of wavelengths that are actually multiples of 400. So, it took 10 years to go a factor of 10. So there's a factor of 10 in the last 10 years. I don't think we're going to see another factor of 10. We're frankly bumping up against some physical limits in terms of just physically how fast we can make things go. But you're going to see at least another factor of 4, and maybe even 5 or 6. And the services that you see are going to be the 100 gig and 400 gig E. And so, another 10 years won't be another factor of 10, but it'll probably be another factor of 4 or 5. And what does that mean? In the last 10 years, we went from 10 gig on wave to 100 gig on wave. So that's an extra 90 gig roughly capacity per incremental unit of the network. Where we're headed for in the next year or two is 400. So that's another 300. And then we will ultimately get to close to a terabit, but it'll be a little while yet. And so we're seeing large capacity changes in the ability of the network to carry traffic. And if you think, it makes my head hurt, but if you think about, even from a security perspective, what it means the bad guys can do to you with a DDoS attack and thing. The networks are great, but they also do a very good job, by design, of carrying the attacks through the network. And so it's another reason why we have to start rethinking about what are the characteristics of the network and what kind of software and security capabilities need to be put in the network, because they have such massive capacities now. So besides the capacity going up, of course, costs are going down. The other thing that's happening is the rate at which the technologies are being adopted is going up as well. There were some macroeconomic trends that drove 40 gig to be a relatively long tail, so that's a bit of an outlier. But 100 gig was roughly 2 to 3 years before. This is just an example. This is not industry wide. This is just for a particular manufacturer, us actually. to ship 5,000 units, but we're relatively representative of other vendors in the industry. So, to ship a certain capacity, total capacity, took 3 years at 100 gig. The 200 gig generation, which has been going for the last couple of years, took 1 3/4. We expect the 400 gig generation to be shipping the same number of units that we did at the 140 gig generation. It took 3 and 4 years. It's going to happen in 9 months. So the adaptation of this is starting. It's really accelerating, and the result is the amount of deployed capacity is just it's the hockey stick that we all see, and we all say eventually it's got to stop because trees don't grow to the sky, and there are physical limits coming, but it's still going pretty fast. Okay? So, of course, speed, everything going faster, bigger, etc. Fortunately or unfortunately, what that does is it increases the complexity of the networks that are required in order to handle all of that capacity. And so, for a while, we can afford to have, and you can draw graphs like this, by the way, for a number of different things. We're going to do this for capacity, but as the overall complexity of the network scales, typically the operational complexity of that scales along with it. Now that works for a period of time, but linear scaling doesn't work in cost. It doesn't work in scale, in physical size, and in terms of operational complexity, it doesn't work either. I mean, you can't hire 10 times as many people to work on your network just because the capacity of that network grew by 10 times. It just doesn't work. So you have to do something to the overall network to basically stop the linear scaling of complexity. The network itself, you can't stop it. It's complicated, right? We're making networks out of chips that rival the complexity of the microprocessors, right? There's millions of lines of code and millions of lines of gates, tremendous amount of complexity that's hiding under the covers of these network systems. And what we have to do is to make those systems usable. We have to abstract and hide that complexity with something. The way that something is intelligence, automation, basically the software elements that are now becoming more and more important of the network themselves. It's akin to going from your regular old POTS GTMF phone that you had probably 20 years ago. And then 10 years or so ago, you had your smartphone, and that was good. But when we went from the basic flip phone to the today's supercomputer in your hand, that was a tremendous amount of complexity there, and we really have to mitigate that with software intelligence so that it's actually manageable to actually use. Right? And again, the way we do that as an industry is with software. And what's happening to the networks themselves is they're moving from fixed function, discrete devices and paths in the network to pretty much programmable elements that can be addressed and changed with software. I mean, there was always a tremendous amount of software in the system just to make them work, but the management and operation of those was, for the most part, manual. You log in your system, you turn up your services, and things pretty much work. But with the kind of scaling that we're having in the network, with the kind of dynamicism that we're seeing in terms of traffic flows and need for different services, we really need to start thinking about the network itself as a programmable platform upon which you build applications that are network-centric. And the kinds of applications we can talk about. Obviously, most of these are operational stuff, power management, spectrum performance, etc. But encryption servicing, partitioning, cloud connect, content servicing, and what I'd like everybody in the audience here to start thinking about is also the same sorts of things that make a network manageable and resilient to change and faults, etc., are also the same sorts of controls that you need in order to adapt the network for security functions as well. And so there's really a lot of synergy in the things that are happening to the network that need to happen to the network just to allow it to do this job, and those which are also needed to improve the security posture. And where we're heading and where the industry is heading is really to start building in some of these security capabilities into the fabric of the network itself, as opposed to having everything being bolt-on security appliances on top of that. Doesn't mean the security appliances are going away. You're still going to need security in various layers of the network, but because the network is as efficient as it is of bringing attacks to people, it also needs to start taking part in the overall security posture of the network. Which kind of drives us to the safer point. The same point we can make about operational simplicity, needing to be there because you can't withstand linear scaling. The more complicated the networks get, the larger the attack surface gets. And again, we can all wish the problem away, but that's not what's happening. The networks are getting more complicated as a result of the complexity. For those, it does require a higher capability. An adversary has to up their game, obviously, but they will. And the complexity that's in the system drives a larger attack surface, drives things that we all want to avoid as cyber warriors and network operators. So again, the same sorts of software and intelligence that can make the operational, break the linear scaling and kind of bend this curve down and make the operational capabilities of the network better and more manageable for the scale of those networks, can also be applied from a security perspective. And when we say secure or safer in this case, we're talking about more than just security in the classic sense, in that you need to be constructing the network out of pieces that themselves are trusted. So and it's getting a lot of press these days. It's not about just the physical supply chain and components that you use to build the network elements that are used to build the network, right? But it's also about the pedigree of the software that goes in there, particularly with the amount of open source software that's being used. You have to consider where that came from, who's been touching it, because again, the complexity is such that it is just not possible. You're not going to do a code review of 500 million lines of code and find the thing that some guy placed in there 5 years ago that shouldn't be there. Or the weakness is through no fault of anybody's own, just somebody made a mistake, and then it's there. So the way you have to solve this is kind of a process-related approach, but you've got to spend time working on both the physical supply chain and the software supply chain. You've got to be dealing, startup industries alive and well. We're all going to be using that, but again, you've got to consider where things came from and how they evolved to be in the system, and a lot, and you just have to do it. In terms of availability, again, things can be perfectly secure, but if nobody uses them, they're so secure that they're so hard to use. Again, that doesn't work either. So the network itself has to be available from an operational perspective as well as a security perspective. So that means making sure that the mission is up. But it also means that to stay available means that when the inevitable happens and somebody attacks you or there's some kind of failure in the network that creates a problem spot, your network has to be resilient enough and have the controls in it so that you can route around those problem spots. And when I say route, I'm actually not speaking about, it could be at the layer 3 perspective, but I'm talking about moving relatively large amounts of capacity around a wavelength at a time. So this is hundreds of gig that we can move around at a time in networks today. And we need to be able to do that in an automated fashion. from a resiliency perspective, as an industry, we've always been good about that. This, when fiber breaks or when there's a hurricane and it knocks down the poles, as long as there's sufficient redundancy in the network, you need to be able to find that excess capacity and move your high priority traffic over those extra paths. So, as an industry, we've always been very good about that, but that still has to be part and parcel, of what's in the network. And then from a security perspective, you've got to make things harder for the bad guys to get in and compromise your network. Try to, the attack surface, regardless of what we do, is large, but you've got to make the effective attack surface as small as possible with the automation and the controls that we talked about. So that's the context that I wanted to provide in terms of why the network is the way it is, how it's evolving, and really the things that we have to think about when we're thinking about networks and what cyber attack is. We're talking about massive networks that can deliver hundreds of gigs, even fairly close to the edge of the network, very quickly. And how do we deal with that? Well, the answer is some form of analytics and software. And so, I'll talk about some of the things that, as an industry, we're doing to help address some of the challenges brought on by the scale, by the dynamicism, by the kinds of capabilities really that the various missions and applications need in the network. The challenge historically, and continues to this day, is to go from a present mode of operations where we're still in the not the higher layers of the network, which have been dynamic for some time, with all the different, layer 3 and above protocols and applications. So that's been relatively dynamic. But the lower levels of the network actually have not. They're starting to move that way for the reasons we've just discussed. But we want to start moving from an arena where, the lower layers of the network, where all the, fairly high capacities are shuffled around, they're still relatively static. We're fairly reactive in terms of when things break, what has to happen in order to fix things. A lot of manual disjointed processes. Historically, security has been bolted on it. It has been, unfortunately, an afterthought. 20 years ago, we weren't thinking about people social engineering and a whole bunch of other things that are happening in the network to cause issues, but it's happened. A lot of the early protocols that were developed, the assumption was you played by the rules. That's really not the way things are evolved. So we've got to start building these capabilities directly into the network. And if we don't do that right, we see this more often than we like to, of course, but it's service revenue is lost or delayed, the quality of service in terms of the user experience and the mission experience suffers, and it costs us, and we expose ourselves to folks with the larger attack surface. Where we want to evolve to as an industry is away from the static models that we have today, which are starting to change. And really what we want to do is, kind of this virtual circle, closed loop process. As an industry where we've been focused first, and this is probably the last decade or so, is what we call programmable infrastructure. So this is, the elements that build up the network itself, the switches, the routers, the optical transport equipment. Much of that was fixed function, a decade or so ago. And we spent the last decade or so getting the equipment to the point that pretty much most aspects of operation are programmable. And they're, we went from proprietary APIs and all that to more industry standard APIs, et cetera. But there's been a lot of work, and we're pretty much coming to the tail end of that, where the infrastructure itself is fully programmable, has APIs that are addressable by software. And so we have the, if we have the intelligence, we have the ability to affect change in the network on a relatively dynamic basis and dynamic in the scale that I'm talking about is, minutes, seconds. Right? Not the days and weeks that historically it has been at the lower levels of the network. You can do truck rolls, and so then back out, move fibers around and pop, et cetera. You really don't have to do that anymore. And again, even though the DoD tends to lag commercial industry, in many places, and in particular, again, in the core, DISA has actually deployed the programmable infrastructure. They're still working their way through and making that available to a lot of the users, but the infrastructure itself is there. More recently, we've been working on, as an industry again, on the control and automation software to take advantage of the programmable infrastructure. So that was the place we went after we had programmable infrastructure. Said, okay, so now we need to take advantage of that. So you'll hear a lot of people talk about orchestration, and orchestration means different things to different people. But at the layer that we're talking about here, orchestration is basically being able to turn up services quickly, to take things which usually were required swivel chair from an op perspective. You're going to get almost managing the systems in 4 or 5 places to turn up a service. You're going to be able to automate that, and so to look at the network resources from a higher layer, or higher level, and then to abstract the network in a way that allows it to be more easily operated on by the users, or by the network operators, really, is what I should say. And that's what we spent the last few years working on. And what we're working on now is really how to completely close the loop. Before it used to be, even though we had programmable infrastructure, there was still pretty much a human in the loop to decide how you wanted to adjust that. Then we abstracted a lot of the information in the network to a higher layer and allowed us to perform more manual operations, but at a higher level more quickly. And so there was automation there. But we still didn't have the ability to completely close the loop and to use analytics and software-based intelligence to do things even more rapidly, to really manage the complexity of those networks. And that's what we're talking about today. Basically being able to close the loop, have programmable infrastructure that has robust telemetry that talks to, some more software smarts, which can analyze the telemetry coming off the network, where the network, really becomes part of a sensor itself, and then can make some smart decisions about what to do, pass the information to the automation software about what it wants to do, and have the automation software, again, push back in and to change the path of the network, adjust the capacities that are available in different places, switch to alternate route because you need low latency, or because it's overnight and you want to do your backups between the data centers. All that stuff becomes now more easily mechanized because of this closed loop control. It's not that you couldn't do it before, but the complexity was such that it was difficult. And so now we're adding the layer of smarts and intelligence to allow that automation to occur in a way that's scalable and in a way that allows it to be used by the non-personnel. And so, in terms of where we're coming from and where we're headed, we've been self-optimizing for quite some time, in the network, in terms of being able to optimize for changes in fiber types and distances and things like that. We've had that for some time. Self-healing, meaning if there's a fault in the network or a fault in the equipment, being able to switch around that and to compensate for those failures in some way so that you can keep the high priority, or maybe even if you've got an redundancy network, all your network traffic up and running. Again, as an industry, we've been able to do that for some time, but that was we did this first, then we did the self-healing, and what we're working on with the analytics and intelligence piece is the self-configuring. I still, even though we're going to have the ability to do fairly complete self-configuring, I don't see us getting away from a man in the loop in some places for quite some time. Just because even though it's desirable from an automation and labor perspective, the self-configuring piece itself can be a fairly sizable attack factor, which you have to consider. So I don't see all aspects of the network being closed-loop controlled, but I do see many of them becoming more and more closely controlled, probably with a switch with a break at some point for certain types of changes the analytics may decide it wants to make. It's going to make a proposal to an operator, and the operator is going to accept yes or no based on their understanding of their higher level tactical understanding of the situation. So that's where I see things going, and consequently, what you'll see is the kinds of software that are necessary in these areas. There's, of course, analytics software. There's various different types of analytics software. Even though there's a lot of work going on just what I'll call native machine learning, where you throw out a bunch of data and it sorts it out and figures out what's meaningful and not. Honestly, I don't see that being tremendously relevant. I mean, we still need to focus the machine on things that are important. We still need people and data analysts and stuff for that. So I see the analytics that we're going to be doing to be more assisted analytics, where we're still using the intelligence of the person in the loop. But then there's a number of things going on with route analytics that, again, using that information to feed into the network. A number of different control applications. MDSL, there's a bunch of acronyms here which I should explain. That's really an orchestration layer. It's a multi-domain service orchestrator. So that's really what you use at a high level to abstract all the information in the network and then to tell it to do something like give me 100 gigs of traffic between point A and point B in the network. You can command it at that level. And it's going to go in and do a lot of low-level things. There's a lot of work going on in terms of network functions virtualization that's using software to provide network functions like routing, like network optimization. I mean, you're not going to do that at the core of the network because it's still too fast to do with software, but towards the edge of the network, a lot of things that historically have been done in dedicated hardware are now going to be done in more general purpose hardware with software running over it. So network function virtualization, again, all the rage these days. It's taking longer than I think a lot of us thought it might, but it's ultimately going to come. But in any event, a lot of software and analytics having to do with both the automation and analytics and intelligence, really the things that you need to close the loop, to automate things, and to bend those curves down that we talked about before that can manage the complexity. Okay? So what is a couple layers of these kinds of software applications look like, and what sorts of things do they do? We could spend an hour or more on each one of these things, but obviously we don't have that kind of time today. So let's just talk at a high level about the kinds of automation software that are necessary to do the things that we just talked about in the previous chart. So if you consider a network that's comprised of, it's a heterogeneous network comprised of a number of different elements, okay, you may have one, your particular favorite vendor of choice there, but you're probably going to have not just one, but multiple vendors worth of the equipment in your network, and you'd really rather not have to manage them all using the individual, sometimes proprietary network management software provided by each vendor. I mean, it's still going to have to be there, but you want to deal with it at a higher layer of abstraction, right? So again, consider a network comprised of multiple pieces, a number of different vendors. These days, of course, they're both public and private clouds that you want to have access to. And then, once you're talking about inside the cloud, maybe you've got some network function virtualization that's either in the cloud or actually, we see that being pushed. The network function virtualization stuff, some can be done in the cloud, but some actually make sense to do at the edge, because at the edge of the network, data rates tend to be lower, a little more manageable, a little more amenable to NFV type of applications. And then what we have to do is we're going to have different elements of software to deal with each of these kinds of things. So you'll have an orchestrator for your NFV functions. You'll have controllers for your different vendors, equipment, and then sometimes you'll have. There's a number of different controllers out there in the industry, and so you may have because of the kind of the history that you have in your network, you may have multiple domain controllers. And again, you don't want to throw this stuff away, so you can have controllers of controllers. As well as a heterogeneous network of stuff. But still, at the end of the day, you have to abstract that into the kinds of things that your network operators can deal with. And yes, of course, they can get down and deal with the individual network elements, but on a day-to-day basis, you really don't want them doing that because we talked about the network is getting so large and so complicated that it's expensive and hard to scale. So what you do is you have a number of different types of collectors, managers, etc., and then you abstract that information into some kind of a multi-domain or network function virtualization service orchestration engine, which has standard definition, which can identify all the different resources that are in the network, and pull it together in such a way that when it's given a command to turn up capacity between 2 points or to move capacity around, or give me a path that's got a latency of less than 100 milliseconds or whatever the requirement is, it has the information in there to do that, and it has knowledge of the lower level devices, issue the appropriate commands to do that. So ultimately we want everything to be constrained in and abstracted in some kind of an orchestration engine. And what's feeding that engine are things like route optimization and assurance, right? There's tons of different paths in the network. What's the best one to go through? There's a lot of different rules associated with that. That in of itself gets to be a fairly complex problem, but at the end of the day, you want to be able to tell the network where you want something to go and how much of it you want to traverse those points, and you're going to need something to figure out what the optimum route is for that. So there's software for that. And then, as I mentioned, there's a lot of information coming off the network, and you want analytics to it, software to analyze that, to process that, and to use that to inform, maybe how the service orchestrator is going to make those changes. And probably should have talked about this one first, but I'm talking about it last because it feeds into the next slide. But one of the base pieces of information, or the base pieces of knowledge that you need about the network, not only in order to effectively use it, but to effectively secure it, is the inventory, meaning what physical devices are out there that are you using to build the network, and what devices are out there that are being used to actually signal across that network. Because really, if you don't know what's out there, you really don't have the ability to control it in such a way to protect yourself, or even to properly operate it. Again, zero trust is another big thing that everybody likes to talk about. If you don't have an inventory, if you don't know who's out there, who they are, what level of security they're at, what they're trying to do, you can't set the appropriate policies even so that you can properly operate the network. So actually, inventory is a base capability that you really have to have in your network, and one that's really important, not just to operate it, but to secure it. And when I say inventory, of course, everybody has an inventory, but a lot of times it's a spreadsheet, a Gonkin spreadsheet that gets old and things change in the field, and you really want to get to a point where the network itself is the database of record in terms of what your inventory is, and you've got automated means of figuring out when there are changes in the network, logging that back. It's a non-trivial problem, and I don't want to oversimplify it or gloss it over. It is a big problem, but solving that really provides lots of benefits, both from an operational perspective and from an ability to protect your network from attack. So, again, from a practical perspective, yes, we can say we need to have accurate inventory, but what's the reality in the field in terms of when you go into a carrier or an enterprise that's operating a network. They've probably been doing this for 10, 20 years, maybe more. So they've got lots and lots of different inventory tools. It would be great if it was just one, but again, the reality is that's not what we see in most of the places. So what you really need to do is look at this, again, holistically. We talked about the layers of the network and abstracting things to a higher layer with some kind of orchestrator. Inventory is the same problem. And then you've got lots of different systems. Typically they're different element management, network management, you've got geographic information systems, all kinds of things out there, including spreadsheets and things like that. And even though it would certainly be nicer if we could start from scratch and just do it all over. Again, there's no do-overs. Nobody's throwing out a decade worth of tools and investments that they just to do it over. I mean, maybe some do, but most don't want to do that. So what you end up doing is a layered approach of what we call and others call is federated inventory. So it's an overlay approach. You try not to throw out things that are working. If things are broken, sure, throw it out. But what you're going to want to do is you're going to basically put a wrapper around the multiple sources of inventory information that you have. Try to automate that, put in verification processes, etc., so that at the top level, you end up with a unified view of all the different types of inventory. And inventory is not just pieces of equipment. Yeah, it's pieces of equipment, but it's also the services that are implemented across those pieces of equipment. And whether those services, sometimes those services are internal, sometimes they're particular customers, and it's tracking things all the way from door to door across the network down to the service level. So it's not just equipment; it's service level inventory that you need, because again, when a new demand comes in, how do you know if you can fulfill it? If you don't have an accurate view of the inventory from the equipment to the services that are rolling over, that are operating over that equipment, you don't know if you can fulfill the demand that just came in. And if you don't know that, you can't automate it. And so that breaks all the things that we're trying to do in terms of simplifying the network operation and improving security posture. So inventory, federated inventory, and the software necessary to, software and services necessary to do that is really key to bending the curve and making the operational simplicity that we need, but it's also key to improving the security posture of the network itself. Okay. All right, so now we have a high-capacity network. We know what kind of inventory we have. So what kind of things can we do from an analytic perspective on the infrastructure itself? Networks are, at the end of the day, they're physical realizations. They have failures, etc. The networks react to those failures. Many times, although as I talked about earlier, not all the time, human intervention is required to fix the problems. We can automatically route around and make adaptations to the network. But at the end of the day, when the fiber gets cut, somebody's got to go out there and fix it. So, there's really no getting around the human intervention piece of it. But we want to try to address some of the long lead times that exist to understand problems, identify their effects, etc. And here's a way that machine learning, artificial intelligence can be used to get a better baseline of what's normal in your network. Right? And so what we want to try to do is, again, failures happen. Can't get around that. But many, not all, life expectancy, predicting that. But many problems in the network are a long time in coming. And if you can appropriately track the network, instrument it up, and track it over time using AI techniques, you can establish what normal is, and you can establish trends. And when you see things moving outside those trend lines that you've established, you actually can get a heads up that something in your network is happening that over time is probably going to result in a failure. So why don't you do something about it now while you have time, rather than wait for the failure. You can wait for the failure, the network will adjust, etc. But it's better for your overall availability if you can address the nascent failure in a maintenance window at a time of your choosing as opposed to waiting for things to actually break. So we can use analytics for that. There's a number of things that we can do on the physical layer in terms of just tracking bit error rates and things like that. The network itself, as I said, is its own sensor in a variety of different areas. And again, if we can trend how the performance of the network is, even at its lowest levels, we can put bars around that and curve fit, etc., and make some pretty good predictions in terms of when things in the network are going to fail, and to give the operators a better idea of when they need to do something about it. That's mostly operational, but from a physical infrastructure perspective, there are also some interesting things that we can start doing in terms of even the physical fiber itself. And as we know, a lot of the cyber stuff happens at the higher levels, but when we start talking about nation states and things like that, you do have to start worrying about the physical integrity of your fiber and if somebody's going to mess in it. And this is an area where you can take, even though a lot of the sensors in the network themselves haven't been designed per se to detect problems in the fiber, these systems are so, in order to work the way they do, they're so finely tuned, they can actually do a pretty good job of identifying problem areas. And so you can use the information that actually comes out of the network itself that it needs just to operate normally. You can pull information with fairly high fidelity, particularly from the coherent modems. These are the devices that put the data on the fiber itself. They're high-speed optical devices. You can use that information to ascertain the health and security status on the fiber. Now, if somebody's done a super job of tapping your fiber, you're probably not going to figure that out that easily. But if they've done things that change the length of the fiber, that change the type of the fiber, any of those things actually can be figured out. And the interesting thing is that there are a very, very rich set of observables that come off these high-speed modems that provide the 400, 500, up to 800 gigs worth of stuff per wavelength. And the systems today, just to operate, they are continuously measuring, we're going to geek out a little here, but some fairly low-level fiber characteristics that are relatively unique to the propagation path of the signal through the network. So think about what you can do and we can do. If you can modify chromatic distortion, that is a analog for the distance that the signal is propagating and the type of fiber that it's propagating over. Same thing for PMD, which is polarization mode distortion. Both these things are analogs for the type of fiber and even the stress that the fiber is under. So by looking at these things in real time, you can start to get a good idea of what's happening to your fiber planner and if anybody's doing anything nasty. It's not foolproof, of course, but it's much better than you can do right now. And then when you add that to, incremental capabilities that we put on mainly to support long-distance transport, right? We can go thousands of kilometers across fiber optic cable now. In order to do that, we've actually had to, have special kinds of amplifiers. But guess what? Those special kinds of amplifiers, they need to have a good idea of what the overall loss profile is of the fiber. So almost all the systems these days have OTDR, that's optical time-domain reflectometry. Complicated name, but basically what it means is we can tell if the fiber has been bent. Of course, if it's been broken, we can tell where the break is. We can get to it faster. But lots of good information in terms of fiber characterizations that can be used at that. Last thing I wanted to talk about is
automated adaptation for traffic demands and control planes. So we talked about things we do in the physical layer. So now if we move up a few layers in the network, what kind of things can we sense there? We can start looking at the flow, different types of video flows or different types of demands that are being put on the network. Even DDoS attacks, which you don't see directly, but you see indirectly because you see these spikes of traffic from a wide variety of areas. You can detect that, and you can use the controlled automation software that we've just talked about to turn up new capacity. And actually, you might want to do that because the new demand is there, but actually, even with a DDoS attack, even though it makes the DDoS attack maybe a little more effective, you've got to reduce the congestion, so maybe you still want to turn up capacity and result in certain kinds of fiber attacks. But basically, using the control abilities that are inherent in the network that allows it to do its job in the first place, you can also use to make it adaptable not only for new types of services and capacities, but also to adapt itself, in terms of some kind of attack. Again, even potentially black hole things that are coming up. You can identify where bad things are coming in. You can black hole it because we've got the adaptivity in the network. All of these things are predicated on analytics, and again, thanks to the near ubiquity of high-speed compute and storage, we can do a lot of things now that just weren't cost-effective before. And again, from a network perspective, pull the large amounts of telemetry, things I've talked about with the modems, et cetera, into an analytics platform, off to a big data cluster if there's that much data that you need, and sometimes there are. Apply machine learning, et cetera, and have a bunch of artificial intelligence-powered applications that are being used to tweak the performance of the network, to identify where there are problem areas, and to overall optimize across multiple different layers. Last thing I want to talk about is network analytics. We talked about analytics on the physical fiber and physical modems itself, but you can also do this analysis on the flows that are going through the network. Figuring out what normal is when there's a mismatch of available capacity to demand, and it needs to be time-based, it's based on the type of service, et cetera. Again, using the analytics and a capacity manager through policy, again, to drive the orchestration engine to adjust the capabilities of the network. And again, all these things you're starting to see in networks today. The root of all this, as we talked about, basically the engine that accepts all the information as well as takes information from, the OSS, BSS, which is the users basically, and these network applications is the multi-domain service orchestrator. This is basically where everything gets abstracted into, and it's really the implementer of both operations and security policies. This is a relatively complex piece of software. It's actually not a monolithic piece of software either, but the orchestrators themselves are getting very complicated as necessary, really, to handle not just the operational state of the network, but also to be able to dynamically implement security policies, et cetera. The kind of use cases that we have for MDSO, we've kind of been talking about them throughout the talk today, in terms of automated provisioning for different network elements in your network, so that when you have to turn up a service which crosses half a dozen different kind of boxes, you don't have to swivel chair into each one of those things. You can automatically do that with the orchestration engine. You can provision across not just different pieces of equipment, but different layers of the network, layer 2, layer 3, and layer 0, 1. Again, historically that was done. All these layers were separated and they were individually managed. Again, with a multi-domain orchestrator, you cross those domains and again make your network more adaptable, more quickly. And then you can even automate across domains, and that's what we're starting to do more of now, right? We've got flows that need to go across the network, but it's got to cross the wide area network, the local area network. We've got virtual equipment that's sitting at the edge. We've got NFV, network function virtualizations in the data center, et cetera. Again, you want to orchestrate and automate amongst all of those. Again, you need software for that. And then the last thing I want to talk about really quickly is awareness at the control plane layer. This is layer 3, right? So this is about as high as a physical network folks we go is control plane awareness, and this is being able to sit on the control plane and actually watch what your layer 3 network is doing. Historically, a lot, and because of protocols, it's all very dynamic. But what you really want to do is you want to be able to do forensic. You want to be able to capture the state of the network at multiple places in time and watch it change. And then when there's a problem, go back and say, well, what happened, to cause my layer 3 routes to change the way they did? So there's a rising group of called route optimization and assurance software, which is looking at the layer 3 control protocols and figuring out what's changed, why it's changed, and to maintain a database based on like a digital VCR, so that you can go back and.
I want to interrupt you for just a second. For those folks that need to get credit, please get your thing scanned because this thing cut off early, which it wasn't supposed to do, so get back here and get it.
Okay. We'll skip to the last chart, which is basically, I think, the future of network automation, which is one that combines high capacity data, lots of control, and the AI and knowledge needed to really automate that in a controlled fashion. Thank you, everybody.
Thank you. Yeah.
Yeah, perfect.